Good morning, everyone, ladies and gentlemen, dear colleagues. Welcome to the 80th Czech lecture organized by the Institute of Mathematics of the Czech Academy of Sciences to honor Professor Eduard Čech, the founder of this institute. I'm proud that we have this long list of distinguished mathematicians who already lectured in this prestigious series. And I think it might be a good idea today to actually introduce Professor Čech and recall who he was. Let me try to switch, yes. So Eduard Čech lived in years 1893 to 1960. When in 1912, he started to study mathematics at the Charles Ferdinand University here in Prague. But his studies were interrupted by the World War I, when he was recruited to the army. But after the war, he finished his studies, and in 1920, he became the Doctor of Philosophy. The two following years, 1921 and 1922, he spent in Italy, where he cooperated with Guido Fubini. He wrote two papers with him there. In 1923, he became a professor at the Masaryk University in Brno, and until the World War II, he worked and lived there in Brno. In 1935, he traveled. He was lecturing in Moscow and Princeton. In 1936, he founded the topological seminar. It was quite well known and established seminar. And this seminar, he continued to run that seminar even after 17th November 1939, when all Czech universities were closed by Nazis. And that seminar was cancelled until quite dramatic circumstances in 1941 by Gestapo. In 1945, after the war, he came back to Prague and taught at the Faculty of Science of the Charles University. In 1947, he became the head of the Research Institute for Mathematics that operated within the Czech Academy of Science and the Arts. This institute was later transformed to the Central Mathematical Institute in 1950, and he was the director of this institute. And 3 years later, this institute was further transformed to the Mathematical Institute of the newly established Czechoslovak Academy of Sciences. After his tenure finished in 1954, he went to the Faculty of Mathematics and Physics of the Charles University. Yes, Eduard Čech was influential and distinguished mathematician. His works in general topology and differential geometry are well known internationally, and we honor him by this series of talks as the founder of our institute. It is my pleasure that the invitation to give the 18th Eduard Čech lecture was accepted by Professor Ramamohan Paturi from the University of California in San Diego. And I will now ask Pavel Pudlák to introduce Professor Paturi to introduce his research and his today's talk. Pavel, please.
Hello, I'm happy to introduce to you Ramamohan Paturi from the Computer Science Department of the University of San Diego. Let me say a few words about him. He first studied in India and got his master's degree in Madras, the city which is now called Chennai. Then he went to the US to do PhD and did PhD under supervision of János Simon at Penn State University. After that, he went to San Diego and became a professor. This was in 1986, and since then he's working in San Diego. He's well known for his research in various fields of theoretical computer science, including communication complexity, circuit complexity, algorithms, satisfiability of formulas, and circuits. He proved some fundamental results concerning algorithms. He's a co-author of the best algorithm for a particular class of formulas. And at the same time, he also proved the best circuit lower bounds. This may sound like strange that working on proving lower bounds and proving upper bounds on the complexity, but it turns out that these two things are very much connected, and improving algorithms often leads to improving upper bounds, lower bounds, and vice versa. Mohan was also involved in administration at the department. He was for several years, he was the chair of the department, and contributed to the fact that today this department is one of the strongest departments in computer science in theory. He also did some practical thing. He founded a successful company called Parity Computing. Today he will lecture about fine-grained complexity, but I will not tell you what it is because this is the content of his lecture. So, the floor is yours.
Okay, so thank you, Pavel. And so I would like to first thank Professor Wychowski and Professor Pavel Pudlak for inviting me and for this opportunity. I'm all set. Okay, thank you. So I would like to say that this Mathematical Institute has been a great place for research. So I have always enjoyed my trip here, and this is my third or fourth trip to Prague, and I'm really thankful for the hospitality here. I would like to specifically thank the staff for all the arrangements, and yeah, it's great to be here. So today we will talk about fine-grained complexity. So let's start. By the way, this is one of very few lectures I'm giving to an audience that is not mostly theoretical computer scientists. So please feel free to stop me and ask me questions. And I set the lecture for 55 minutes, and so there's plenty of room for questions. Okay, so let me start with computational complexity. Okay, so this is the study of the computational resources required, like time, space, and randomness, to compute problems. Okay, and so what's the purpose of this theory or this complexity field, which is, if you ultimately think about it, the purpose is to guide the design of efficient algorithms for concrete problems. Okay, so the theory is very much connected to the practice, and you want to help the designers. So today my goal is to present the theory of fine-grained complexity, which is a branch of the computational complexity. I will explain how it differs and what progress has been made in this field. Okay. So many times I use the word complexity. So what that really means is a function of the parameters of the problem instances to time or space or randomness. Okay, it's a measure of the difficulty or easiness of the function. Okay, so let me tell you what a theory here is. Okay, so what's a complexity theory is about? What are some of the basic ingredients? So we start with the problems and classes of problems. That's our playing field. And we have algorithms and design techniques for developing efficient algorithms, or sometimes not so efficient algorithms. So then it looks so far discrete. So you have these separate problems and their separate algorithms, and they have all different complexities. And what makes the theory a more interesting theory is the notion of reduction among problems, or complexity relationships among them. Okay, so that's an important notion. That's what makes the theory kind of hold together. So then once we have the notion of a reduction, we have the notion of a hard or a complete problem. And then we have conjectures about the hardness of problems. And we have conditional lower bounds. Okay, so if you look at the tenor of this, if you look at the tenor of the list, I am talking about conditional lower bounds and conjectures. So what has been the case is that so far, no non-trivial lower bounds have been proved on the computational resources required. And P versus NP is one of the celebrated problems. But so even for simpler problems, no non-trivial lower bound has been proved so far in a reasonable computational model. So given that, so we are left with the choice of developing the theory that can explain the potential behavior of the complexities. So that's why the conjectures play an important role. For example, P is not equal to NP. Okay, so let me, just to get traction for the rest of the lecture, one important concept is reduction. So let me briefly talk about reduction. So you have problems, think of them as all separate and discrete instances, discrete objects, but you want to understand the relationships between them. And so we have this notion called problem A is reducible to problem B. Oh, there's a typo there, okay, by reduction F. If so think of each problem as a language of strings, okay, or as a decision problem. Decision problem means there are only two answers for each input. It's a yes or no. So you can think of the problem. So you can identify the problem with the yes instances. So what the reduction does is that so given an instance of the problem A, and whether we can tell whether X belongs to A if and only if f of X belongs to B. Okay, so that's what a reduction is. So this is a transfer of one instance of one problem into some other instance of the other problem, such that the decisions are tied together. So to obtain meaningful complexity relationships, we need to limit the computational power of F. If the reduction itself is very powerful, we cannot obtain useful conclusions about the problems. Okay, so for example, we can limit the reduction to be polynomial time, and such reductions are called polynomial time reductions. Okay, so for example, under polynomial time reductions, we can say that if A reduces to B, and if B is polynomial time computable, then so is A. So that's a usefulness of the reduction. Okay, or contrapositively, you can say that if A is hard, that means if A is not polynomial time computable, so then B is also not polynomial time computable. So this is what creates the theory, and this is the most important concept. And let me very quickly give you the most classical theory, which is NP theory, or the theory of NP completeness, and tell you quickly what are the ingredients, what are the key objects in this theory. Okay, we have celebrated NP complete problems, and satisfiability, independent set, Hamiltonian path, and so on, so forth. And we have important classes. P stands for polynomial time computable problems, and NP stands for non-deterministic polynomial time computable. So that means this is the class of problems which, when given a solution, the solution can be verified quickly. So that's one way of thinking about it. Okay. So the important notion of complexity relationship is a polynomial time reduction here. And So the basic result in this NP theory is that all these so-called problems, famous problems, they're all equivalent as far as polynomial time computability is concerned. That means if one of them is polynomial time computable, then so is every one of them. And if one of them is not polynomial time computable, so then no one else is. So that equivalence is the key result of this theory. Okay. And there's also these problems. There are also the complete problems. A simple problem like 3-SAT, which I'll explain in a second, is complete. Means that if this problem can be solved in polynomial time, then every problem in the class can be solved in polynomial time. Okay, so that's basically gives rise to the conjecture P not equal to NP, and this is the famous conjecture, and so we can get conditional lower bounds if P were not equal to NP, then none of the NP complete problems have a polynomial time algorithm. So this is the rough structure of a theory, complexity theory, and what we are focused today is a more fine-grained or more refined version of the theory. Okay, so we are not interested in polynomial time equivalence of the complexities. That's good, but we are interested in specifically whether something can be computable in n square or n cubed time, or 2 to the n, or 2 to the 10n, or 2 to the 2n. So we're interested in the specific complexities as precisely as we can, and we don't make any distinction between deterministic or randomized algorithms, and we want to develop complexity relationships that focuses on exact complexities. The kind of questions we ask is that, so typically you have exhaustive search or a standard algorithm for computing a problem. What improvements can we make over this exhaustive search? That's a typical question. And what abstractions are there to limit improvements? So if we cannot improve an algorithm, and there must be some abstractions, can we point to those abstractions? And can we come up with some principles that explain the exact complexities? Okay. Part of the reason I'm talking about principles and abstractions is that we only have a guess at these, of course, guess at these abstractions. So we have not been able to prove that certain thing is an abstraction for improving the efficiency of algorithms. Okay. So basically it differs. So the two theories differ in the following way. The fine-grained complexity is focused on NP specific problems and exact complexities, and it requires more fine-grained reductions to develop this theory. Polynomial time equivalence is not sufficient. Under polynomial time equivalence, n squared and n cubed and n to the 10, they're all the same. 2 to the n, 2 to the n squared, they're all the same. So that's what is required. And so before I go further, not to make this talk more abstract, I would like to introduce some concrete problems that people care to solve, and I give some concrete algorithms for those things. Okay. So let's start with the simplest problem. So we have a collection of sets from a universe, and two collections of sets, and you want to know whether there is a pair of sets, one from each family, such that they are disjoint. Okay. So this is called orthogonal vectors problem, for the simple reason, if you view the sets as characteristic vectors in the of 0, 1 to the size of the domain, that being of course empty set being the intersection is equivalent to that the vectors being orthogonal. Okay. So therefore given a set of 0, 1 vectors, do there exist a pair of them such that the dot product is non-zero? Okay. So clearly there are two parameters were of interest. So the number of vectors or the number of sets and the size of the universe. Okay. So we use both the parameters to characterize the complexity of this problem. So if you think for a few minutes, you will come up with two straightforward algorithms. One is n squared times log d. You compare. So you take each pair of vectors and compute their dot product and check if it is equal to 0 or not. That can be done in n squared log d. A slightly different way of looking at the same thing will give an algorithm that is 2 to the d times n. If D is small, that's much more effective. Okay, when D is order log n, so the second algorithm does not prove to be that effective. Okay, so the question is that can we improve upon this? Can we improve upon the standard algorithm? Sorry. Okay, so it turns out there's a lot of cleverness in designing algorithms. Many clever people, many smart people have used many clever ideas to design algorithms. So I'm going to present a very quick idea of this algorithm that improves upon this n square, so the standard n square algorithm, by a tiny bit. So where D is C times log n, and you can improve upon the exponent by 1 over log C. And this is a non-trivial algorithm, highly non-trivial, and it uses a series of tricks. Okay, let me go through this one to tell you to give you a flavor of there's so much cleverness possible. Therefore, given that, now how can you prove lower bounds that certain things cannot be accomplished in certain time? So that's the challenge complexity theories face. So let me introduce one more problem in the same category before I go to the algorithm. So three-sum problem. So you are given integers in some domain and taking values in some domain. Now, once again, do there exist three numbers such that two of them sum to the third one? This is kind of similar in flavor to the previous one. Both can be solved in n squared time. And the question is, so there is more cleverness possible, and you can improve upon this n squared log d. And the question is that all these are these two problems both seem to take n squared time. Are they related? Okay. So these are the kind of questions we'll be asking. And before that, let me present the algorithm. Okay. So the technique we use, there are many techniques in this orthogonal vectors algorithm that gives a savings of 1 over log C, so over the standard n square algorithm. And we name the key technique is polynomial method. So that's why it's called polynomial method. So this is the theorem. We can improve upon this standard method by a savings of 1 over log C, of course, in the exponent. And this is a randomized algorithm. And so there are three key ideas, okay, for designing this particular algorithm. One is to find a meta problem, a problem that is kind of mother of many other problems, okay, that for which we know of improvement over the straightforward calculation. And that meta problem in this case is the matrix multiplication. Matrix multiplication, the standard n by n matrices, you can do it in n cubed time, but there have been development. So there have been results that show that you can do faster than n cubed. And matrix multiplication is a kind of meta problem because many problems can be cast as matrix multiplication problems. So then we use the polynomial method to reduce this orthogonal vectors problem to a polynomial, from the polynomial to matrices, from the matrices to matrix multiplication. And then we use some simple techniques of load balancing to optimize the parameters to get n to the 2 minus 1 over log C. Okay, so let me provide some more details. And so the first step is that take the vectors, divide them into n over s blocks, and where s is a parameter. And so basically, we don't want to tackle a large size problem. We want to divide into sub problems of smaller size first. Okay. So let's define a function which is orthogonal vectors. Take these two S vectors, and then answers 1 if and only if there is a pair of them that are orthogonal. Okay. So now what we're going to do is that we construct a polynomial with a small number of monomials to approximate the orthogonal vectors problem. Okay. So this polynomial outputs the correct. This polynomial outputs the correct output with probability at least 2/3. That's a property. I will show you how to do this in a second. And so given this tool of this approximate polynomial, this is what we're going to do. For each pair of problems, for each block of inputs, AP and BQ, that's in fact AI and BJ. So we're going to compute an approximate polynomial, and so then each polynomial will be evaluated by using matrix multiplication in time s squared times polylog s. So that means the matrix multiplication is giving the answer for a set of S inputs, of course, in each block. Okay. And then we choose S carefully. Okay. So to get an overall complexity of n to the 1 minus, just n to the 2 minus 1 over logs. Okay. And the probability of correctness of the overall algorithm is at least 2/3. Now we can repeat this experiment about order log n times by increasing the poly log n with one more factor log n to get the probability to be arbitrarily close to 1. Okay, so this is somewhat detailed plan, and the two key steps are, now how do you convert a function like orthogonal vectors into a polynomial with small number of monomials, and how do we convert the polynomial into a matrix multiplication problem, and then there are standard fast matrix multiplication algorithms that they all fit together to give us this improvement. So let's talk about Boolean expressions to polynomials. So we take a field of 2 elements and we express. So the key here is that if you take the orthogonal vectors function with S input, 2 S inputs, and each one is a vector, you can represent it as a simple Boolean formula. Okay, so think of each 0 and 1 as a Boolean value, and when the corresponding bits, both of them are 0, when the pth bit is 0 in both vectors, so then their complements both will be, So when the pth bits both are 1, so then their complements will be 0, so then the AND will be 0. Okay, so therefore the dot product is implemented by these complements and disjunctions, and then you sum it over, or you take the union over all pairs. Okay, so this is a simple formula that evaluates for each pair of vectors the corresponding dot product. Okay, so what we are going to do is that we take this simple formula, we approximate each of the disjunction, both the disjunction and the conjunction by polynomials using while controlling for the number of monomials. Okay, the key here is that the small complexity of the orthogonal vectors problem gives rise to an approximation by using a small number of monomials. So what's the key idea here? So this idea is due to Rasborov and Smolensky, and so let's focus on disjunctions for now. So let's say you have a function which is a disjunction of functions fi. Okay, we are going to approximate it as a GF2 polynomial, where we replace the disjunction with a parity sum. And the parity sum will have coefficients, and the coefficients are randomly chosen. So that means I'm replacing this Boolean formula with an expression, with a linear expression in GF2. Okay, so what is the connection between G tilde and G? G tilde equals G for any X with the probability at least half. Okay, why is that? So if G tilde is 0, that means each of the Fi are 0. And the linear sum of them is also 0, no matter what the random bits are. But on the other hand, if G of X is 1, that means at least one of the Fi must be 1. Condition on that random sum will be 0 with probability half and 1 with probability half. So that means we can discriminate whether there is at least 1 with 50% probability. So that's the start of the thing. So then what we're going to do to improve the probability, we take several random copies of G tilde and take the disjunction. If one of them is 1, so then the function will be 1. If all of them are 0, the function will be 0. So the basic property is that if you take this function h, that's equal to the G with the probability 1 minus 2 to the minus t. So we have boosted the correctness probability by using this repeated, by using the repeated trials. Okay. So now we can again convert, say, every Boolean expression can be written as a GF2 polynomial, and so we can now T will allow us to control the degree. So notice one thing, Q is a much larger number. We started with a large disjunction, and now we can control the size of the disjunction by using T. And we don't need T to be too large. We need T to be something like log Q. And then ultimately we can write the whole thing as polynomial. And the number of monomials is controlled. Okay. So that's basically it, and we start with this OV function, and we can approximate AND by using the same technique by converting AND into to an OR by using De Morgan's law. Now we can put all these things together. We'll approximate the ANDs with the T equals 2 log S, and the outer disjunction with the T equals T to obtain the final polynomial. And this final polynomial will be correct with probability at least 2/3, and the number of monomials for this value of S will be can be made to be arbitrarily small. Okay, so that's basically we go from simple Boolean expressions to polynomials with a small number of monomials. Okay, so now this is the next technique we need. Now, how do you go from polynomial to matrices? Okay, so let me give you the sketch of this proof. And what we have is that we are going to reduce the polynomial evaluation to fast matrix multiplication. Okay, so we're going to construct two matrices given the polynomial. Think of the polynomial as a sum of monomials, and each monomial can be expressed into. Okay, we're going to create two matrices. The first matrix is indexed by the vectors A sub I. The rows of the first matrix are indexed by the vectors A sub I, and the columns are indexed by the monomials. Okay, and so the entry of this matrix is, you evaluate the X part of the monomial. Remember, the monomial is a product of variables. There are some X variables, there are some Y variables. So you do the partial evaluation of the monomial based on the information you have from the vector A sub I, which corresponds to the X variables. So similarly, you construct M sub B, where the rows are indexed by the monomials and the columns are indexed by the vectors B sub I. And now the content of this matrix is the same monomial evaluated on the second half of the input. Okay, now observe, if you do the matrix multiplication simultaneously, so each entry of the matrix of the product matrix will give you the dot product, or will give you the value of the polynomial. So that means simultaneously you can compare all the pairs and then evaluate the polynomial at each of the pairs. Okay, and once you have this one, so notice that the number of monomials form the one of the sides of the rectangular matrix we have, and it's important that it be a rectangular matrix so that we can efficiently evaluate it. So there's a classical theorem of Copper-Smith that shows rectangular matrices can be evaluated much faster. So this is not n cubed, this is more like n squared. So when you put all these things together, we get the desired improvement in the exponent, which is 2 minus 1 over log C. So you see that so we have used a variety of techniques. Load balancing, taking a larger problem, dividing that into sub problems. That's what we call load balancing. And then you have approximation by polynomials. Then of course, then evaluating the polynomials using fast matrix multiplication. So the point here is that so a lot of cleverness was required to improve the exponent by a tiny bit. What more improvements are possible? What other clever ideas are waiting for us? That's the tantalizing question. Okay, let me pause here and let me move to a different type of problems. Okay, and these are the NP complete problems. And so the most celebrated problem is the satisfiability problem. And I'll briefly explain what it is. We have a circuit or a formula on n Boolean variables. And for example, take conjunctive formulas. It's a conjunction of disjunctions of literals, and the complement of a Boolean variable is also a Boolean variable, and together they're called literals. And so the basic question is that given a formula or a circuit, does there exist an assignment which satisfies all the clauses or which outputs 1 for the circuit? Okay, so that's a basic question. And so obviously you can solve it with exhaustive search. For each possible setting of the variables, so we can quickly evaluate the formula or the circuit in polynomial time or polynomial in the size of the formula, and then multiply and then figure out whether it is satisfiable or not. So that is the basic exhaustive search. The basic question is that can we, of course, is there a more clever way of figuring out the satisfiability than trying out all possibilities? Okay. And so that's the question. Can we improve the exponent even by a tiny bit or by a constant, depending on the parameters of the formula? And that constant is called the satisfiability savings. And this could be a function of the various parameters. And that's the central question in this. And satisfiability, as you know, that it's NP complete problem, and the best known algorithms in the general case are no faster than 2 to the n. Okay. So what I'm going to do is that I'm going to look at a very special class of satisfiability, which is conjunctive formulas, and show you by using some simple ideas we can improve upon the exponent. Okay, so I'll give you the next algorithm. And so the example I take is KSAT, which is disjunctions of literals. So disjunctions, conjunction of disjunction of literals, where each clause has at most k literals. So that means, of course, in general, the clause does not have any limit on the number of variables in it. But here we are going to limit it. Okay. And even with such a limitation, even for k greater than or equal to 3, such a problem is NP complete. When k equals 2, this can be solved in polynomial time. From 2 to 3, the complexities seem to jump significantly. Okay, can we solve at least KSAT or 3SAT faster than 2 to the n? A lot of effort has been put into this very question, and several ideas have been developed. So I'm not going to say much about it. So the best known algorithms are called PPSC style algorithms, which itself is based on so-called PPZ algorithm. So I will explain what these two abbreviations mean, and these are the authors by which these are the initials of the authors by which these algorithms are known. Okay, and so the first algorithm was partly developed when I visited Prague 1990s. Okay. So what I would like to do is that I would like to spend a few minutes explaining the basic PPZ algorithm. PPSC is a lot more complicated. That will take multiple lectures. And so this is the algorithm. Okay, this is what we call Davis-Putnam style algorithm. So what you do is that you simply try all possibilities. Okay, and hope for some savings. Okay, so what we do is that we start with a CNF, which is the input, take a random permutation of variables. We order the variables randomly. And when you cannot guess or when you cannot figure out the value of the variable, then you set it to both 0 or 1, or you set it to 0 or 1 with equal probability. When you don't know, you simply toss a coin. But sometimes you might know the value of the variable. That happens when you have a clause with only one variable in it. That's called a unit clause. When you find a unit clause, there is no need to toss a coin. Simply set the value of that variable as dictated by the unit clause. That gives you a savings of 1 bit. And if you're lucky, you will get many unit clauses in the process, and you can save many bits. That is the key to the efficiency of this algorithm. So this algorithm always outputs the correct answer. Sometimes it won't output anything. And so that means whenever it outputs an assignment, it's a satisfying assignment. And we can turn this so this probabilistic algorithm into an algorithm that takes more time, but then produces answer with much higher probability. Okay. So turning this into an algorithm, So we have a constant success probability in time 2 to the n times 1 minus 1 over k. So basically n over k is the savings we obtain for this algorithm. So over exhaustive search. So let me give you the proof of this one. There are only 2 or 3 ideas needed for this basic algorithm. And by a satisfying solution, I mean a set of course, a setting of the variables that satisfies all the clauses in the KCNF. Okay, and we say that a satisfying solution is isolated provided its distance 1 neighbors in the Hamming cube are not solutions. Okay, so I will give an example in a second. So that means these solutions are isolated in terms of Hamming distance. So let's assume you have a CNF, a KCNF with an isolated satisfying solution. And it turns out at the isolated satisfying solution, all the clauses must be satisfied because it is a solution to the formula. And moreover, it so happens that there are clauses with exactly 1 true literal and the rest of the literals being false. Those are called critical clauses. So critical clauses are those that are barely satisfied to make the whole formula true. So for example, so let's take this formula. Okay. Of course, given the setting 0, 0, 0, which is a satisfying solution, and at that satisfying solution, the formula has 3 clauses which are critical. The first 3 clauses are critical. The first one is critical for x2, the second one is critical for x1, and the third one is critical for x3. So if you basically, in other words, if you were to flip x3, the formula will be unsatisfied. So therefore, if you start with an isolated solution, you can guarantee critical clauses at the solution for every variable. What's the advantage of critical clauses? And if you know, of course, if the variables are ordered in the right way, if you know the first 2 variables in the critical clause, which are set to 0, then you know the last variable must be 1. So you don't have to guess the value of the last variable, provided the first 2 variables, which are 0, come before the last variable. So that means if the ordering is such that the critical variable comes last, then you can get some savings. So that is essentially the analysis. And we compute the probability that this PPZ algorithm outputs a satisfying solution based on the number of neighbors which are not solution. So let's take a satisfying solution. So let's assume that it has at least I of x neighbors which are not satisfying solutions. Of course, if x is isolated, I of x equals n. Okay. So what we look at the following probability, the following event. What is the probability that that at least for so many variables, I of x over k variables, that the critical variable appears towards the end of the list of variables in the critical clause? Okay, and we show, and the second probability, the second event is that what is the probability we assign correct values to the other variables that are not critical? Okay, so if you look at these 2 events, the probability of the first one is at least 1 in n by using Markov's inequality. And so the reason is that if you randomly order the variables, so for each critical clause with probability 1 in k, the critical variable will appear as the last variable in the list of the k variables. So therefore, on average, so you have n over k or in fact I of x over k variables that will appear as the last variable. So the probability of the average number of appearing as the last variable is at least 1 in n. Once they appear as the last variable, we need to set the other variables correctly, and the probability of that is 2 to the minus n plus I of x over k. So putting these things together, probability that x is output by PPZ is the product of these 2 probabilities. Okay, so that's exactly that. Okay, so so then we can go from here and then show that, okay, we only looked at isolated solutions, and if you use some simple isoperimetric inequalities, we can conclude that no matter what the formula is, And as long as it is satisfying, that one of its satisfying solution will be output with the corresponding probability. There may only be one satisfying solution, and then in which case it is output with its probability. And if there are many satisfying solutions, the probability can be improved. Okay. So by repeating this algorithm several times, we can output the correct assignment quickly. Okay. So that's basically the key idea behind the PPZ algorithms, and a lot of work has gone into improving upon that one. But nevertheless, this is still the current best approach. And so these are the constants for 3SAT, 4SAT, and KSAT in general. So those are the best results so far. And there is a small improvement in the second or third decimal by Shader recently in the value of mu sub k and mu sub 3. And it turns out under mild assumptions that mu sub k is no more than 2. Okay, so this is what's known. We don't know whether this is the optimal algorithm. This may be far from optimal or maybe close to the optimal, who knows. Okay, so this is the state of the algorithms, and let me quickly okay, so let me introduce a few more problems that are NP complete to complete the rest of the presentation. So Hamiltonian path. So given a graph, does there exist a path that covers path of length n-1 that covers all the vertices exactly once? Okay, that's a colorability given a graph. Can we color the graph with k or fewer colors? Similarly, a chromatic number, and you have maximum independent set. What is the largest independent set of a given graph? These are all very famous problems. They're all NP complete. And so the question we can ask is that, can we expect similar improvements in the exponent for solving these problems? Now that we have solved K, C, and F with a small improvement, what can we say about these problems? Okay. So, okay. So now let's reset ourselves. We have seen two algorithms. A lot of effort has gone into developing these algorithms, several decades of work. And where do we go from here? What can we say about the rest of the problems? Can we keep improving these things? And so we can at least start asking questions. Okay, can we improve the orthogonal vectors problem? More specifically, provided that D is omega of log n, so that means the dimension is increasing faster than log n, can we find a fixed constant epsilon such that orthogonal vectors problem can be solved in subquadratic time? Okay, that's a question. We don't know the answer. Okay. Similarly, we can ask the same question for the 3-sum problem. Okay, and we can ask similar questions for the satisfiability problem. So you have seen 3SAT can be improved to 2 to the 0.386 times n. Can we improve it further? Can we keep improving the exponent for the satisfiability for the 3SAT problem such that it goes to 0? Okay, and let's define this constant as sub k. These are the best exponents for solving the KSAT problem. So the question is that, can we keep improving the 3SAT problem? That does not mean P becomes equals to NP. So there could be a sub-exponential algorithm for 3SAT of the type 2 to the n over log n. Okay, so and what's the limit of these constants? Or we can ask a different type of questions. If orthogonal vectors problem can be solved faster, means subquadratically for large enough dimension, what can we say about the KSAT? So if you notice KSAT, so the exponent or the satisfiability savings seem to decrease as k increases. So it behaves like 1 in k. Can we find a fixed constant such that KSAT can be solved in time 2 to the 1 minus delta times n? Okay. Are these two problems related? They seem to have similar flavor. Okay, that's the question. Similarly, we can ask even simpler question. What's the connection between 3SAT and 4SAT? If 3SAT can be solved in sub-exponential time, 4SAT means each clause has at most 4 literals. Can 4SAT be solved in sub-exponential time? And what about 3 colorability versus 3SAT? Are they related problems? can improvements from one transfer to improvements to the other. So these clever algorithms give rise to many other questions for other related problems, and the purpose of the fine-grained complexity is to be able to link these results and to provide some guidance about the complexities of other problems, of course, assuming the complexity of certain other problems. Okay. So let me quickly say that what we need to develop a fine-grained complexity theory is not, so we need an important notion of reduction. This is again the key for the theory. The kind of reductions we need are more fine-grained. We should be able to transfer small improvement for one problem to some other problem. Whereas polynomial time reductions are too blunt to make these small distinctions. So we need a different kind of reductions where the complexity parameters, where the number of vertices or the number of variables, number of clauses are preserved, of course, in a linear fashion. So if you look at the standard reductions for NP completeness, the parameters blow up polynomially. So that will not help us to draw conclusions about the fine-grained or exact complexities of various problems. Okay. So what we need is a linear preservation of parameters, and so let me give a simple example. This is a very standard reduction, and so we can ask the following question. Let us say 3 colorability has a sub-exponential algorithm. That means 2 to the epsilon n for arbitrarily small epsilon as n goes to infinity. Does it imply a sub-exponential time algorithm for 3 SAT? So what the standard approach would be, so you take so we are asking for a kind of easy problem imply an easy problem. Okay, so therefore we need to reduce the so-called hard problem 3 SAT to 3 colorability. So if you look at 3 SAT is a formula. So each clause has at most 3 literals. The number of variables is n, but the number of clauses could be n cubed. Okay, so when you reduce a formula to a graph, the number of variables becomes the number of vertices becomes the number of variables plus the number of clauses. Therefore, for the graph you get in the reduction, you will have roughly n cubed vertices. So therefore, polynomial time reducible, okay, sub-exponential time is not preserved in this kind of reduction. Okay, so what we need is a reduction that preserves the linearity of the parameters. So that means an n variable formula, we should be able to reduce it to a graph with n vertices, or at least constant time and many vertices. So that requires a new type of reduction techniques, and that is the key message I would like to give in the rest of the talk. So it turns out it's not clear such linear time preserving, so linear parameter preserving reductions are possible in polynomial time. Okay, what we're going to do is that we're going to use more powerful reductions, but preserve the parameters. Previous reductions, polynomial time reductions, they only use polynomial time, but they blew up the parameters by polynomial amount. So now we're going to use a different trade-off. So we use a lot more time, but we try to preserve the polynomial parameters linearly. Okay, so for that purpose, we have this notion of a sub-exponential time and sub-exponential time reductions. Let's not worry about it. The key idea is that take a problem and transform into another problem, not just one problem, but sub-exponentially many problems with where the parameters are preserved, but you can use sub-exponential amount of time. So here we are trying to study exponential time algorithms so we can allow sub-exponential time reductions while preserving the parameters of the problem. Okay. So this is the key lemma and if there's one central lemma for this theory of fine-grained complexity, this is it. This basically shows you can take a 3 SAT formula which may have n cubed clauses, and in sub-exponential time, you can rewrite it as a union or a disjunction of linear size or linearly many clauses, formulas with only linearly many clauses. So that means we take a dense formula, write it as a sub-exponential disjunction of linear size formulas. So with this, we can preserve the parameters. Okay, and so there are two places where sub-exponential time comes into play. The time this particular reduction takes sub-exponential time, and the number of problems it generates, one problem becomes sub-exponentially many problems, but with the parameter of the problems controlled significantly. Okay, so I will not go into the proof of this one. This is a branching program, and it uses a fairly sophisticated argument to limit the size of the tree to conclude that we will not create subproblems without control. Okay. So now that we have the sparsification lemma, now we can go back to our reduction. We can reduce 3SAT to 3 colorability. So let me show you how to do that. So you start with a 3CNF and apply sparsification lemma. So you get sub-exponentially many formulas, and each with a linear number of clauses. And take each formula phi sub I with linearly many clauses, write it as, or reduce it to a graph. So graph with only linearly many vertices, linearly many edges. Then ask whether that graph has a 3 colorability, whether it can be colored with 3 colors. That will inform the satisfiability of phi sub I. So then we can do this, try it out for each of the sub-exponentially many sub-problems, and then figure out the satisfiability of the given formula. Okay, so the key factor we are using is that we only have linearly many clauses. Therefore, we can convert a formula into a linear size graph. Previously, the formulas had n cubed many clauses. So the same idea can be used to reduce 4SAT to 3SAT under sub-exponential time. So 4SAT has n to the 4 clauses, up to n to the 4 clauses. But once we sparsify, we get sub-exponentially many 4SAT formulas, but each with a linear number of clauses. And we can use the standard trick. A 4 clause can be written as a conjunction of 2 3 clauses by introducing an extra variable. But the number of extra variables that we need is linearly controlled. Therefore, we change the number of variables by a linear factor and converted 4CNF, which is a more expressive formula, to a less expressive 3CNF. Of course, it required sub-exponential time, and in the process, we generated sub-exponentially many instances. Okay, so therefore, we can conclude if 4CNF can be solved. So it can be solved in sub-exponential time. So then we can conclude if 3CNF can be solved in sub-exponential time, so can 4CNF. Okay, so this is the key idea. So let me not go into the details. So let me focus on. So what we have shown is that satisfiability, 3SAT plays an important role, and what the previous theorem actually shows is that if 3SAT has a sub-exponential time algorithm, so then all the problems in a very large class called SNP also have a sub-exponential time algorithms. So we tied, excuse me. Okay. So we tied the sub-exponentiality of the 3SAT to the sub-exponentiality of many other problems. So that kind of gives some evidence their fate is all linked together. So either they all have a sub-exponential time algorithm or none of them do. So this gives us some courage to make the following hypothesis called the exponential time hypothesis. And it basically says that the constant S3 is strictly greater than 0. This is based on the fact that the best known algorithms support this, and it will be very surprising if you find a sub-exponential time algorithm for this problem. But who knows, there may be one. Okay, so what can we do with this assumption? So what's the point of making the assumption? So starting with this, can we explain the complexities of other problems? So that's the point of this one. Of course, if we can prove this or disprove this, that will be a great result. That will be even stronger than P versus NP. And even if we cannot disprove or prove this one, can we make some progress? And that's what that's the plan. So what kind of explanatory power does this hypothesis have? And one important thing to notice is that we don't even fully understand quadratic time algorithms. We don't even understand quadratic time algorithms. And exponential time algorithms have a lot of power. We can use a lot of cleverness in designing such algorithms. And for this hypothesis to be useful, if we can provide, so the essence of what is the essence of exponential time? And using ETH, can we factor out the difficulty of exponential time and then explain the complexities? So that means, is there one single principle that can explain the exponential complexities? And ETH would be a candidate for such a principle. And unfortunately, it turns out no one principle is sufficient at this point, but ETH seems to have a fairly good track record. Okay, so I will so just flash this result saying that there are many problems in a large class of problems that all of them have a sub-exponential time algorithm, do not have a sub-exponential time algorithm provided ETH is true. Okay, so that means one assumption will explain the sub-exponential time complexity of many other problems. Okay. So there's a whole bunch of other related problems which are also not expected to have sub-exponential time algorithm provided you believe the exponential time hypothesis. Okay, fine. So let's look at one more. What is the nature of these constants as sub k as k increases? Okay, so we proved, Russell and Polyazon, and I proved that this constant increases infinitely often. We know that we can solve satisfiability in time 2 to the n times the size of the formula. And the satisfiability savings behaves like 1 in k. So as k goes to infinity, of course, the limit based on the current algorithms, the limit is 1. But what we were able to prove is that this must increase infinitely often. It could be that limit is strictly less than 1. But there's no evidence to support that. We make a stronger hypothesis called a strong exponential time hypothesis that says that S infinity equals 1. So that means as k goes to infinity, the best exponent you can expect for solving k sat is 1. The limit of the exponents is 1. Okay, so this is once again, so this problem, okay, so this statement is not an isolated statement. There are many problems which will achieve their exhaustive such equivalent complexities once you believe the strong exponential time hypothesis. This also has significant explanatory power. Okay, so let me show one example. Okay, so we talked about orthogonal vectors problem, and we asked whether there is a subquadratic time algorithm for it. Now I will show under strong exponential time hypothesis that orthogonal vectors problem cannot have a subquadratic algorithm. So we are connecting a low complexity problem like orthogonal vectors with a high complexity problem like satisfiability. Okay, so this is what I call the explanatory power of a strong exponential time hypothesis. You see the connections between various problems. One complexity can explain the other complexity. Okay, so let me give a sketch of this result. So let's assume that so this is a high level plan. We assume that there is an efficient algorithm for orthogonal vectors when the dimension is increasing faster than log n. Okay, what we do is that we take a k-sat problem, reduce it to orthogonal vectors, okay, such that each clause of the KCNF corresponds to a coordinate of the vector. Okay, so let me give let me give a little bit more detail. So let's assume the variables in the formula come in two colors, red and blue. For each color, for each setting of the variables, we'll derive a vector from the set of clauses. So for example, let's take one clause. The formula itself is a conjunction of clauses. So if you take one clause, you have two types of variables, x and y. Let's take a setting alpha for x, setting beta for y. And now we can define, so the ith component of the vector to be the evaluation of the part of the clause at alpha and part of the clause at beta. So you get two vectors. So if you look at the, of course, I negate the variables, okay? And if both parts are 0, so the negations are 1. Therefore, the dot product is 1. So therefore, I'm able to convert the formula evaluation problem to an orthogonal vector problem. So more details, okay? So let me give you the quick detail here, and we start with this orthogonal vectors problem where epsilon does not depend on the constant in front of log n. There is no constant in front of log n. That constant is growing as n grows. So we have a growing constant, so to speak. So, but whereas epsilon does not change with the constant in front of log n. So we take some parameter epsilon prime. So we start with a KCNF, and we sparsify it first to have many instances with only linearly many clauses. And we divide the variables into two groups of n over 2 variables. For each group of variables, we'll get 2 to the n over 2 settings. These are the 0, 1 assignments for each group of the variables. But we're not going to look at all the settings at the same time. We look at the settings for each group separately. So we only have 2 to the n over 2 possible settings. 2 times 2 to the n over 2 possible settings, which is far different from 2 to the n. Okay. So now we can argue using the previous technique, we can come up with 2 families of sets. Remember, these families are exponential size. And the formula phi sub I is satisfiable if and only if there is a pair of sets such that their intersection is empty or their dot product equals 1. Okay. And the total time it takes is that capital N. So there is sub-exponential time you need for or exponential time. So control exponential time you need for doing all the pre-processing, for doing all the reductions. For computing the orthogonal vector problem, you need subquadratic time. So capital N is 2 to the n over 2. Therefore, if you plug in the parameters, you are able to show that KSAT can be solved in 2 to the 1 minus epsilon over 6 times n, where epsilon is independent of k. The key idea here is that, okay, so k does not influence epsilon because orthogonal vectors problem has a fixed epsilon. So therefore, this implies the strong exponential hypothesis is false. Therefore, we can conclude that orthogonal vectors problem does not have a subquadratic algorithm, assuming strong exponential time hypothesis. So this is the connection, and just to conclude. So we asked this question, and can we reduce orthogonal vectors? Okay, can we connect the complexities of the 2 problems? Of course, yes, we can connect without any conditions. Okay, and can we connect the complexities of 3 SAT and 4 SAT? That also can be done. And can we connect the 3 SAT and 4 and 3 colorability complexities? That also can be done. Okay, and now we can look at the connection between 2 different problems. Okay, can we connect the complexity of orthogonal vectors to the complexity of the KSAT? And the answer is that if the strong exponential time hypothesis is true, then there is no subquadratic algorithm for orthogonal vectors. Okay, so this kind of gives you the flavor of the fine-grained complexity. So to summarize, we need fine-grained reductions so that we can transfer the easiness or the hardness of one problem to another problem without changing the parameters too much, while preserving the linearity of the parameters. That means small improvements in one problem can be transferred to small improvements in the other problem. Okay, and for doing that, we need this falsification lemma. That's what enabled all these reduction, most of the reductions, So clearly there are many open problems. Prove or disprove the exponential time hypothesis. So the nice thing is that either one is a great result, will be a great result. There will be no disappointment. So if it is false, great, we have great algorithms. We have faster algorithm for satisfiability. So it's a win-win situation. Okay, that's the nice thing about complexity. And if you have hard problems, then you can have cryptographic protocols too. So there's no loss here. So just understanding them is a key thing. Similarly, can we prove or disprove strong exponential time hypothesis? Let me pose somewhat more nuanced question. Okay, let's assume one of them is true. So let's assume ETH is true. Can we prove a specific bound on S sub 3? Can we prove a lower bound on S sub 3? Can you prove that S sub 3 is at least 1/4? Okay, or can we prove S infinity equals 1 assuming ETH? What are the abstractions for proving this? So that will be the next theory to develop, in the sense of why can't we have reductions that will enable so these kind of results? Or can we ask, assuming KSAT or strong exponential time hypothesis, can we also prove a lower bound on the colorability problem? Turns out the satisfiability and colorability, while they are related, there seem to be some fundamental difference between the two problems. What's the connection between the two problems? So there are many, many open questions, and the field is wide open, as you can see. And the conclusion is that we understand very little about the exponential time complexities or polynomial time complexities of very basic common problems. Okay. So thank you.
Are there questions or comments? Yes.
Well, first of all, thank you very much for a very nice lecture. It was illuminating for me as a non-specialist. So I have a naive question. You know, I was always puzzled by the role of randomness in this field. Now it's a little bit better after your talk. I'm not so puzzled. But still, on your first slide, you mentioned that randomness is a resource for computation. Please, can you explain me in what sense it is a resource?
Right. So one thing, so if you look at a randomized algorithm, okay, so it's using time and space and random bits. So the more random bits are needed, so that means that more resources are needed. Random bits ultimate. So let's think physically. Random bits need to be generated by someone through physics, let us say. So that's a resource. So therefore the question is that, can we compute that algorithm using the fewest random bits? That also makes it possible to make the algorithm more deterministic. So if you allow too much randomness, so then it's less valuable, both physically speaking, from a practical perspective, and also from a theoretical perspective. That makes it more difficult to de-randomize it. Okay. So there are many deep results in this field due to my colleague at Russell Impaliazzo and Avi Vigderson, that shows that this is so this randomness as a resource is very much connected to some of the complexity hypothesis.
But one should also say that from the practical point of view, that there are some problems that are solvable by randomized algorithms very efficiently, but there are either no non-randomized algorithm for the problems, or they are not so efficient.
So yeah, so that's an interesting comment. And in the beginning, several years ago, the best known algorithm for primality, or at least polynomial time algorithms for primality, are randomized algorithms. Okay, until about 10-15 years ago, there was a polynomial time deterministic primality algorithm that kind of reduced, that kind of showed that randomness is not essential. Right now, the best candidate that benefits from randomness is polynomial identity testing. So given a multivariate polynomial, does it ever produce? Of course, is it always equal to 0? Okay. So whether it's identically equal to 0. So that means the polynomial is not necessarily given as a, of course, in the monomial fashion. So then it's easy. So let's say it's given as some kind of complicated expression. Does it always produce 0? So it's not clear whether we can. So there's a fast algorithm with randomness, and we don't know of a fast algorithm without randomness.
Are there more questions?
Yes. So when you're looking at P and NP, a basic thing is all the machine models are equivalent. So you can switch between Turing machines and register machines and whatever in polynomial time. Does this become an issue again with fine-grained complexity, which machine model you're using?
Not much of an issue because most of the models have a logarithmic, unless so they have logarithmic relationships, you get some extra log factors. So take random access machines and as a model of computation, and all reasonable models are within log factors. So if you want log factors, then you need to be even more careful. Right now, we are focusing on polynomial factors and to the, of course, quadratic versus subquadratic. So the log factors can be absorbed into the subquadratic.
And I've got a related question, which is in this classical complexity, you define all these classes of problems and look at relations between them. How come we don't see that here? So you started off with these two problems that are somehow reducible to matrix multiplication, but there's no diagram of problems with a set of problems reducible to matrix multiplication.
When you look at the problems from a distance, they all seem the same. That's how we got P and NP. When you look at them more closely, so take, for example, the three-sum problem and orthogonal vectors problem. Okay, they both can be solved in quadratic time. And if we look at them closely, they don't seem to belong to the same class by any reasonable definition of the same class. One can be done, so three-sum can be solved much faster by using co-non-deterministic algorithm. So there seem to be a lot more diversity in terms of the complexities. So if you want to have classes, they need to be fine-grained classes to preserve these things. There seem to be many classes. And for example, SNP is one such class. There is a class here. And so one way to define classes is that all the problems that are reducible are equivalent to the orthogonal vectors problem, three-sum problem. They all define classes. So that's why what I was saying is that in this theory, problems define classes.
Okay.
So there are deeper computational phenomena happening underneath these problems. And it's not clear how to capture them by using machine models.
Questions? Let me just add a comment that Mohan presented just two problems for which he considered fine-grained complexity, but there was a host of problems that people analyzed in this way. And in fact, that there was a whole semester at Simons Institute in Berkeley devoted to it.
Pavel is wearing the T-shirt from that semester.
Okay, so if there are no other questions, then thank you very much again.
All right, thanks a lot. It was a beautiful lecture. So we are closing the lecture now. And I wish to thank all online speakers, all online participants to be with us. So thanks a lot.